The flange includes 54 precision-machined threaded holes for high-strength stud installation. Nozzle shell rings include coolant inlet and outlet nozzles with diameters of 850 mm and 300 mm. Support shell ring provides structural support for the vessel. Central shell ring, designed to withstand neutron irradiation. Lower shell ring and bottom head support core fuel assemblies. Coolant outlet temperature, 328.9 degrees Celsius dimensions, height 12 meters, width 4.5 meters, weight 334 tons, service life 60 years. The process begins with smelting and forging high-strength perlitic steel 15 Chi 2 EMFA. Ingots weighing up to 360 tons are prepared and shaped using presses with a force exceeding 15,000 tons. This stage provides the structural foundation for the reactor vessel. Forming the bottom head requires a double-action forming press with a tonnage over 15,000 tons, enabling precise shaping under extreme pressure. The process ensures uniform thickness and structural integrity to withstand operational stresses. Mechanical treatment involves advanced cutting, CNC machining, and surface grinding to achieve exact specifications. Plating is applied to improve corrosion resistance and durability. Rigorous dimensional inspections verify compliance with design standards, ensuring the bottom head meets operational requirements. The manufacturing and testing process of a reactor vessel, specifically for a VVER-1200 nuclear reactor, involves multiple stages to ensure durability, safety, and performance. Assembling and welding. In this stage, components are assembled and welded to form the reactor vessel structure. The process ensures seamless integration of parts, maintaining structural integrity under high pressure and temperature conditions. Heat treatment enhances the mechanical properties of the steel. The reactor vessel components are heated to around 650 degrees Celsius to relieve stresses, improve strength, and ensure long-term performance under operational loads. Advanced non-destructive testing techniques, including X-ray control, are used to detect potential defects such as cracks, metal burnout, sponginess, and inhomogeneity. High-resolution imaging scans the vessel's internal and external surfaces to identify three-dimensional defects. Hydraulic pressure testing. To validate the structural integrity of the pressurized equipment, hydraulic pressure tests are conducted. The procedure includes filling the vessel with water, generating test pressure, and monitoring instruments for leaks or ruptures. The generated pressure ranges from a minimum of 254 atmospheres to a maximum required value. The tests confirm that no metal ruptures or leakages are present. LD Machinery's precise engineering and rigorous quality control processes ensure that the VVER-1200 reactor vessel meets all safety and performance standards, supporting long-term operational reliability in nuclear energy applications. The production process begins with the creation of the rocket's core components. Large aluminum plate stock is used to create the skin panels for the fuel tanks and other key components. These plates are loaded into one of 4 double gantry skin milling machines, where they are precisely milled into patterns that will form the base of the tanks and other parts. This milling process reduces the original weight of each aluminum plate by 70% while maintaining 75% of the material strength, which is crucial for the rocket's structural integrity. Once the skin panels are milled, they are transferred to the brake form and bump press stations, where they are shaped into curved sections that will make up the barrels of the fuel and oxidizer tanks. After shaping, components made from aluminum undergo anodization, a chemical process designed to protect the material from corrosion. The anodization process involves high-pressure washing of the components, followed by a series of chemical baths that seal the material. One of the most critical steps in rocket production is the welding process used to assemble the fuel tanks. ULA utilizes friction stir welding, FSW, a unique technique that uses a rotating pin tool to generate heat and stir the parent material, effectively welding it without the use of filler material. The friction stir welding process is used to join the aluminum skin panels into barrel sections for the fuel and oxidizer tanks. The Delta IV and Vulcan Centaur rockets require 5 panels for their tanks, while the Atlas V tanks are made from 4 panels. Once the barrel sections are welded, they are moved to the circumferential friction stir welder, where domes are welded onto each end of the barrel, completing the first stage of the fuel tanks. After welding, the tanks undergo pressure testing to ensure the integrity of the welds. Once the tanks are complete, they move to the spray-on foam insulation SOFI booth, where they are coated with a layer of foam insulation. This insulation protects the tanks from the intense acoustic vibrations during launch and helps maintain the temperature of the cryogenic fuels. Following insulation, the tanks move to final assembly, where they are integrated with other components such as wiring, engines, and avionics. The entire rocket is then fully tested to ensure all systems are functioning properly before being prepared for transport to the launch site. Once the rockets are fully assembled and tested, they are transported to the launch site for final preparations. ULA's rockets are typically transported by ULA's specially designed cargo boat, the RS rocket ship. The rockets are shipped from Decatur to either Cape Canaveral Space Force Station in Florida or Vandenberg Space Force Base in California. This transportation process takes up to 23 days, depending on the destination. United Launch Alliance, ULA, is a leader in the space industry, known for its reliable and accurate space missions. The rocket production process at ULA is a highly sophisticated and meticulous procedure, ensuring the rockets meet the rigorous standards required for both national security and space exploration missions. This process begins in ULA's 1.6 million square foot production facility in Decatur, Alabama, which serves as the heart of ULA's manufacturing operations. Steel production begins with the preparation of essential raw materials. The primary inputs include iron ore, coal, and limestone. Iron ore, often sourced from Michigan mines, provides the fundamental element required for steel production. Coal, converted into coke, serves as a carbon source and fuel for melting processes. The blast furnace, known as the C blast furnace, is the heart of the steelmaking process. Rebuilt in 2007 with the latest technologies, this furnace operates 24/7 and can produce up to 6,000 tons of molten iron per day. Raw materials, iron ore, coke, and limestone, are loaded into the furnace from the top, while superheated air is blown into the bottom. The furnace operates at temperatures reaching 4,000 degrees Fahrenheit, initiating chemical reactions that produce molten iron. This molten iron, known as hot metal, is then tapped and transported in insulated bottle cars to the basic oxygen furnace, BOF, for further processing. In the basic oxygen furnace, the molten iron is converted into steel. Before pouring the hot metal into the BOF, scrap metal is added, typically forming 25% of the mix, with the remaining 75% being molten iron. Pure oxygen is blown into the molten mixture at rates exceeding 21,000 cubic feet per minute. This process removes carbon impurities, melts the scrap metal, and forms liquid steel. The result is a highly refined steel ready for further treatment. The steel is then poured into ladles for transport to the next stage. Electrodes are used to reheat the molten steel, while alloying elements are added to achieve specific properties, strength, flexibility, or corrosion resistance. The LMF ensures precise control over chemistry, cleanliness, and temperature. This step guarantees that the final product meets the desired specifications required by customers in industries like automotive manufacturing and construction. For applications requiring ultra-low carbon steel, the ladle may undergo additional refining in the vacuum degasser. This process involves exposing the molten steel to a near-absolute vacuum, removing dissolved gases such as hydrogen, nitrogen, and oxygen. After refining, the molten steel is sent to continuous casters for solidification. The steel is poured into an intermediate vessel called a tundish, which feeds the liquid into water-cooled copper molds. As the steel flows downward, it solidifies into long rectangular slabs with dimensions customized to customer requirements. These slabs are further cooled using a fine water mist and cut to the desired lengths by gas torches. Barcoding ensures each slab is tracked through subsequent processing steps. The slabs are reheated to over 2,300 degrees Fahrenheit and processed through the 7-stand hot mill to achieve the required thickness. Initially, the slabs pass through a scale breaker to remove surface impurities before entering the roughing mill. The roughing mill reduces the slab's thickness from 8 inches to 1.5 inches. The steel then moves to the 7-stand finishing mill, where it is further reduced to the desired gauge, which can be as thin as 0.07 inches. The steel exits the hot mill as a coiled ribbon, up to 4,100 feet long, and is cooled using water sprays to meet mechanical property requirements. These coils can be shipped directly to customers or sent for additional processing. For applications requiring cold-rolled steel, the hot-rolled coils are processed in the pickle line tandem cold mill, PLTCM. This state-of-the-art facility, launched in 2011, combines pickling and cold rolling technologies for enhanced precision and surface quality. The process begins with acid pickling, which removes any surface scale left after hot rolling. The steel then passes through 5 rolling stands equipped with 6 high mills to achieve precise thickness and surface finish. An automated inspection system ensures the coils meet quality standards. The final coils can be sold as cold-rolled steel or sent for coating and galvanizing to enhance corrosion resistance. Step 1. Shearing. The first step in bolt manufacturing is cutting the steel rod, known as round bar, to the required length. A shear, similar to a guillotine, chops the bar rather than sawing through it. For smaller bolts, a Peddinghaus shear is used, capable of cutting up to 2-inch diameter and 100-inch long bars. Step 2. Heading. Next, a hex head is formed on one end of the steel rod through a process called hot forging. The end of the rod is heated to approximately 2,000 degrees Fahrenheit using an induction coil. Then a machine called a national upsetter shapes the heated end into a hexagonal head using dies and clamps. After forming the head, it is stamped with the manufacturer's logo and grade symbol for identification and quality assurance. Step 3. Chamfering. Before threading, a chamfer or bevel is added to the end of the bolt using high-speed cutting blades. Step 4. Threading. The threading process involves cutting threads onto the bolt using Landis threaders. These machines use rotating heads with cutting tools called chasers to remove steel and form precise threads. A continuous stream of cutting oil lubricates the process to prevent overheating and maintain sharp cuts. Caustic soda. The bolts are submerged in caustic soda to remove grease, oils, and other organic materials accumulated during manufacturing. Sulfuric acid. After cleaning, the bolts are dipped in sulfuric acid, which removes rust and scale while etching the steel surface to prepare it for zinc bonding. Flux. Finally, the bolts are treated with a flux solution, which ensures proper adhesion of the zinc coating. The bolts are then dipped in an 840 Fahrenheit molten zinc bath for 2 to 4 minutes, followed by spinning in a centrifuge to remove excess zinc. Once cooled, the bolts are inspected, painted for identification, packaged, and prepared for shipment. This process guarantees that each bolt meets industry standards and is ready for long-lasting performance in structural and industrial applications. Danieli's high-tech steel production line is a state-of-the-art facility designed for efficient and high-quality steel manufacturing. The process begins with a continuous billet caster specifically engineered for hot charging. This system is capable of producing low and medium carbon steel billets with precise dimensions of 150 by 150 mm square profiles. The process begins with a continuous billet caster specifically engineered for hot charging. This advanced caster operates with high thermal efficiency, minimizing reheating energy requirements. It ensures seamless transfer of billets to the induction furnace, reducing oxidation and improving surface quality. Designed for precision, it supports continuous casting with consistent temperature control and uniform solidification, ensuring metallurgical integrity and reducing downtime. The system is capable of producing low and medium carbon steel billets with precise dimensions of 150 by 150 mm square profiles. The billets are then transferred to an induction furnace, ensuring optimal heating before entering the roughing mill. The roughing mill features 6 SHS single housingless stand units, which provide structural rigidity and flexibility for high-precision rolling. Following the roughing stage, the material advances through the intermediate and finishing mills, which ensure the desired dimensions and surface quality are achieved. An advanced inline quenching and tempering (QTB) treatment system is integrated into the line, allowing for the production of high-strength deformed bars. These bars are treated to enhance mechanical properties, including durability and resistance to stress. The finishing speed of the system reaches an impressive 12 meters per second, enabling high production efficiency. Once cooled, the bars proceed to the cold cutting to length system, which uses a precision cold shear to cut bars to specific lengths. To further streamline the process, the line includes advanced bar counting and bundle forming equipment. Bars are grouped and bundled into lengths ranging from 9 to 15 meters, with individual bundle weights of up to 4 tons. Weighing and collecting services are seamlessly integrated to ensure accuracy and efficiency in handling and transportation. Hot forging is a manufacturing process widely used in the production of metal components, particularly for applications that require high strength and durability. It involves heating metal, typically iron or steel, to a temperature where it becomes malleable and can be shaped under pressure without cracking. The process begins with the preparation of raw materials. Steel bars are stored and organized based on their dimensions and material properties. Each bar is encoded with a barcode and monitored digitally to ensure traceability throughout the production cycle. Once prepared, the bars are loaded onto a conveyor system and welded into position for entry into a heating furnace. Inside the furnace, the bars are heated to precise temperatures, measured by optical pyrometers to maintain consistency and quality. After reaching the desired temperature, the heated bars are cut into segments of the required size. These segments are then pre-formed in a press to create a rough shape that closely resembles the final product. This preforming step is critical as it prepares the metal for the final shaping process. The main forging process is carried out using high-power hammers, or magli, which exert forces ranging from 16,000 to 31,000 kilogram meters (kgm). These hammers shape the heated metal into precise forms based on customer specifications. The forged parts can weigh between 15 to 200 kilograms, making the process suitable for producing large and heavy-duty components. One of the challenges in hot forging is controlling vibrations generated by the powerful hammers. To address this, modern forging facilities incorporate anti-vibration systems that reduce ground vibrations by up to 90%, minimizing environmental impact and improving workplace safety. Once the forging is complete, the parts go through a trimming process to remove excess material, known as flash, using trimming presses. The trimmed components are then transported via conveyor belts to designated storage bins, ensuring efficient handling and organization. Quality control is an integral part of hot forging. Each component undergoes a thorough visual inspection to detect any defects. Advanced monitoring systems and automated machinery further enhance precision and consistency throughout the production process. In addition to its efficiency, hot forging is highly customizable.